Good afternoon, ladies and gentlemen. If I can get my panel assembled here, we'll get started. This is the assembly of ancient dinosaurs who are looking forward to recounting their experiences over the past decade. Gentlemen, their experiences over the past decade with, wow, okay, maybe I'll stand over here and I won't do that. With the creation of the ARPANET and then the internet that followed. And so what I hope to be able to do in this hour and a half is get these pioneers to regale you with some of their experiences, their observations, their insights, and perhaps even some speculation about where do we go from where we have now gotten with this story. My name is Vince Cerf. I'm Vice President and Chief Internet Evangelist at Google. To my left and your right is Steve Crocker, who is the CEO of Shinkuro, but he and I were graduate students at UCLA in Len Kleinrock's lab. Len is sitting right there to Steve Crocker's left. Bob Kahn is next, and David Walden. Bob was variously at MIT, Bolt, Beranek, and Newman, and DARPA, and now at the CEO of CNRI, the Corporation for National Research Initiatives. Dave Walden had most of his career at BB&N, I think, and you can correct me and add things if you like. Len Kleinrock migrated from MIT in the early 1960s to UCLA, where he has become a permanent fixture and produced an enormous number of graduates whose primary focus has been the mathematical behavior of distributed systems. So I'm going to ask Len to begin because it was his exploration of queuing models of packet switching, message switching at MIT that gave some insight into the behavior of these kinds of distributed store and forward systems. But Len, I'd like to ask if you would explain what it was that drew you to that particular problem, because it wasn't exactly on everyone's front door that they needed to understand these systems. So why did that turn out to be a topic of interest to you when you started your research?
Well, at MIT, I was surrounded by computers. And most of my classmates were working on problems regarding information theory and coding theory, really hard problems, which weren't leading in any magnificent direction. And being surrounded by computers, I recognized sooner or later they're going to have to talk to each other, and there was no effective technology which would allow that to happen. The telephone network was woefully inadequate. So I decided to create a model and try to analyze what would it be for data traffic to move in a network. What were the issues? How could you model it? How could you analyze it? How could you optimize it? And at that time, I developed the mathematical theory of data networks. And nobody cared. There was no application. AT&T said it wouldn't work, and even if it did work, they said they wanted nothing to do with it. And you wonder why. And the reason is, when I think back, there was no data to send. There was no business model. They couldn't make any revenue on this thing called data. So the theory was developed. At the same time, at Rand Corporation, Paul Barron was doing a similar thing, looking at military networks, which would be basically robust against an attack. And this theory lay there until, as we'll discuss in a few minutes, ARPA decided they needed a network. And so the theory was waiting, the need was there, and the next step was to implement this. And I'm sure you can pick that up with the rest of the panel.
So one interesting factoid is that some of these people have been colleagues for quite a long time. Do I remember correctly, Bob, that you were at MIT when Len was there, or did you arrive after Len went to UCLA?
Len would probably have to pin it down. Probably he left before I got there, because I arrived there in roughly September of 1964, and I believe he left shortly before, but he can
I think that's right. You got to UCLA.
I left in August of '63.
Yeah. So, but MIT figures rather strongly in this picture. In particular, three of these people. David, were you at MIT as well?
I was at Lincoln Laboratory, MIT Lincoln Laboratory.
Close enough. So what you basically have here is the four horsemen of the apocalypse from MIT in one way or another. So you've done this analysis. One of your colleagues is Larry Roberts, who was at Lincoln Laboratory and was drawn by force to ARPA in the mid-1960s to go run this ARPANET project. And the motivation behind building the network was not to build a system that would, survive a nuclear attack, which is what some people misunderstand. Paul Barron was working on that problem at RAND. But what Larry Roberts was asked to do is to figure out how to build a network that would allow multiple computer science departments funded by DARPA to share their computing resources. Every one of the departments said we need a world-class computer every year to keep up their quality of their research, and even ARPA couldn't afford to buy those machines for every university. So they said, we're going to build a network and you're going to share. Larry came down to ARPA in the Information Processing Techniques Office in order to initiate that project. And that emerged as a request for quotations in 1968. And by this time, if I am remembering correctly, Bob Kahn, you left MIT and were then at BB&N, is that correct?
You want the exact time? Maybe
no, yes, I would like it within a millisecond. But I'm trying to figure out the relationship between you and Dave Walden, who was at BB&N at the time this request came out. BB&N was one of many responders. There's a tiny irony here. Steve Crocker and I were graduate students in Len Kleinrock's laboratory, and we worked with another company that responded to the RFQ, but we lost. So you had a hand in responding to that RFQ.
Yeah, we did. But before I specifically answer that, let me just also say, Larry Roberts recently passed away, and Len organized with one of his sons a very lovely memorial service out there. Larry was a prime mover in making the ARPANET happen. I mean, I kind of view him as the mastermind of what actually happened. But absent that, Larry would be here today and probably give you the definitive view of it from a DARPA perspective. From my perspective, I got involved in it sort of tangentially. I never thought I'd be involved in that project right from the get-go. When I had gone to BB&N, I had taken a leave of absence from MIT. And the reason was I was sort of viewed both within MIT and I think even within parts of BB&N as more of a mathematical theoretician guy, sort of maybe more like Len, I guess, I don't know. But the fact of the matter is I thought taking a leave of absence made sense because I could work on a real problem rather than solving some equation or working on some theoretical things. And that's what I had understood from Jack Wozencraft, who ran the group, to be essentially getting tenure at MIT. Show that you can do something that makes a difference. And when he and I talked about what that might entail, he said, why don't you take a leave of absence for a year or two? This was not his attempt to get me out of there, because he and I remained friends for a long time until he died. But go get some practical experience and come back, which is what I intended to do. And when I got there, I was working on computer nets without even knowing what DARPA was. I wasn't aware of it. And they had just gotten the DARPA contract. I think Danny Barbara was the PI on natural language communication with computers. And Danny said, fine, you want networking? Go for it. And I think part of it might have been funded out of that contract, part of it might have been funded overhead charges. I started working on networking, and Danny's boss and my boss was a guy named Jerry Elkind. And Jerry basically one day said, why don't you take that set of reports? It's like that high. Things like flow control, congestion control, all the kind of things you worry about networking, and send it to DARPA, which I did. I thought maybe they'd be interested, but it never occurred to me that it would make any difference there. It was more my development. And then I got a call back from Bob Taylor, who said, could you come down and visit? And that's how I got to know who DARPA was and learned that they were planning a network. And when they finally put out that RFQ that you talked about, which was not a request for proposals interesting, it was a request to quote building a 4-node net.
Like buying a pencil or something. As if it was an off-the-shelf item.
It was not quite off the shelf, but it landed on my desk. And I was not in a position to really a gentleman that had just been hired into BBN named Frank Hart showed up, walked into my office, and he also reported to Jerry Elkind, and he said, you know, I understand you have this RFQ from DARPA. Can I see it? My answer was, who are you? I mean, I didn't know who he was. And one thing led to another. I ended up collaborating with him and some of the people working with him, including Dave, on actually writing the proposal to DARPA. I still have my handwritten draft of that proposal that we sent in, which was something that came to fruition by my working with another fellow in that group named Severo Ornstein, who dealt with all the hardware stuff. And eventually we put in a full-blown proposal, and it won. So that's my coupling into that group. And
you mentioned Frank Hart.
We won the award.
You mentioned Frank Hart, another one of the BB&N guys who passed away recently. But there's still a bunch of us that are left, and we're still plunging along. So, David, how did you get drawn into this thing? You were part of Frank Hart's group. Yes, David.
Well, in 1968, which is when the request for proposal came out, I was 26 years old. I'd been at BB&N for about a year and a half. BB&N's a place where they would hire people not quite knowing what they would do if they wanted them. And I had come from Lincoln Lab, and Frank Hart hired me there. So BB&N received the request for quotation according to the stamp with Jerry Elkind's stamp on August 9th. It had come out in late July. As Bob mentioned, BB&N's upper management placed the job in Frank's division, where Severo Ornstein, a hardware guy, and I, a software guy, already were in Frank Hart's group. And as Bob described, Bob came across the bridge from the other computer division, and we began to sit together. And we began to design and plan a system design for the IMP, and also an implementation plan, because we were going to make a proposal to build something. The four of us, plus a bunch of other people at BB&N, almost finished that proposal. A lot of other people kibitzing and making comments and trying to make it one that would be more readily accepted from the government. But a little while before the proposal was due, Will Crowther, another person who had been in Frank's group at Lincoln Laboratory, and my mentor, we recruited him because, frankly, being not so old and with only 4 years experience, I thought we needed Will. We needed another person who was a more experienced real-time programmer. And Will helped refine the proposal. The proposal went in on September 9th. That's when it was due. It might have gone a few days earlier. And we waited. A while longer, I'm not sure how many days or weeks, we got a call to come to ARPA and answer questions about our proposal. And Bob, Frank Hart, Severo Ornstein, and Will Crowther went down to ARPA. They came back. They sounded to me like they thought they had a good meeting. And then some more time passed. My memory is, and Bob can correct me if I'm wrong, we were designing and thinking all along. We never really stopped that much, kind of informally. Before the end of the year, we were notified that we were going to get the contract, and on January 1st of 1969, we began funded work. We worked through the first 2/3 of the year, the hardware guys getting the hardware interface designs. Ben Barker had joined Severo in the hardware side of things by this time. Out to Honeywell, we were going to use a Honeywell 516 computer to fabricate the interfaces using their electronics technology. Bernie Cosell joined Will and I on the software side, and we began implementing. And of course, as you implement, you continue to design. Bob was there, and he had meetings with us and helped us think about things. By the way, I forgot to mention this. When Bob first came over from the other division, he was giving Severo and me little tutorials in networking because he'd been thinking about it already as part of our meetings. Do you remember that? It's true. So we, even though we'd never done networking before, had a real resource nearby that could help us get up to speed. We knew about real-time programming, but we didn't know about networks. So at that point, we spent the first 2/3 of the year doing the implementation. Bob spent a lot of time working with the phone company and working on documentation and in general working on the 24-bit cyclical redundancy check in general, doing whatever needed to be done. And by September, where we had a delivery date, we were able to deliver the first IMP, the first packet switch to Len Kleinrock's group at UCLA. And we delivered the next one to Stanford Research Institute, the next one to UC Santa Barbara, the next one to the University of Utah. And by early December, basically one every 3 weeks, that network was operational. There were 4 nodes now which could communicate. As each IMP had gone in, the host people would begin to try to make their interfaces work with the IMP. The user computer people made their interfaces work with the IMP. Now we had a 4-node network, which my assessment is it demonstrated, at least at a demonstration level, the efficacy of packet switching. And it also provided something where the hosts could begin to try to talk to each other and so on. A lot of people have favorite dates late in 1969 for when it all started. For instance, the UCLA meeting and the announcement for this meeting, like the day when a message was sent from UCLA to SRI. I like the date when there were 4 nodes in the field, because in my mind, that was the beginning of a revolution in research and network research and network implementation. And it certainly was the making of my career.
Well, I think everybody who's ever had anything to do with projects of this scale have different milestones that they remember, especially, and that one's yours. I do have to remind you of a story. When BB&N won this contract, they got a message from Senator Ted Kennedy congratulating them on their ecumenical effort, because he had misunderstood that what they were building was an interfaith message processor instead of an interface message processor. So there was a reason that the first packet switch was sent to UCLA, and that's the reason is sitting right over here, Len Kleinrock. So can you say a little bit about what it was about your job or your work at UCLA that caused the first node to show up there?
Sure, and in answering that, I can fill in a little bit of the pieces that came up in the rest of this discussion. MIT Lincoln Laboratory is mentioned. They played an essential role both in my education. They sent me to MIT. They sent Larry Roberts to MIT on a full scholarship, and we were office mates, Larry and I. And that's where Larry began to see a lot of the work I was doing on networking. There was a lot of sharing among the PhD students. And Frank Hart came out of Lincoln Lab. Lincoln Lab provided a lot of the talent that eventually gave rise to the ARPANET. So you think about this proposal that was sent out, or this request for quotation, and how was it generated? When Larry came to ARPA, unwillingly, as you suggested, he was dragged there, and happily he was, we had to put together a specification as to what this thing was we were going to ask for a quotation on. And so a bunch of us got together and started laying out what this would be. For example, they wanted the system to appear like a time-sharing system to the users at any node. And the point was made, if it can't respond in half a second, this is not a good enough network. So the spec was put in that the response time for short messages should be no more than half a second in the spec. Question is, it should be reliable. Well, to make it reliable, you could play the game that ATT did and said, it'll be 99.99959's reliability, which is immeasurable. There's various definitions as to what that means, but it's not practical. We decided it should be such that if any node or any line fails, everybody else can communicate. That's called a two-connected topology. It's a very practical and theoretically provable capability. It was put in. And when I was there and I said, look, if we're building an experimental network, we better build in measurement tools. This is an experiment. Be able to test a network, generate traffic, collect the traffic, trace packets, etc. So that software for making measurements and pushing things through the network was built in as part of the spec as well. So now to answer your question, what I just described is why UCLA was chosen to be the first node of the ARPANET. It's because we had the tools available to test the network, understand the theory, make models, anticipate what should happen, and then prove experimentally that it did or did not. And if not, why not? So UCLA was chosen to become the network measurement center of this evolving and emerging ARPANET.
So it turns out that I mentioned earlier, Steve and I were graduate students working for Len in his laboratory. And Steve ended up being the founder of what is now called, or was the Network Working Group. This is just an informal collection of graduate students at many of the different universities, all to become part of this ARPANET. And he has the problem of trying to figure out how to get all the host computers that connect to this homogeneous network to interact with each other. So my recollection is that you were hoping that the machine that they were sending from BB&N would be delayed because it was the Labor Day weekend and they airshipped it instead. Would you like to just expand a little bit on your role in all of this?
Yeah, you bring back vivid memories. BBN was a very organized professional group, and those of us who were distributed around at the various sites were considerably less so. First IMP was coming to UCLA, and we were feverishly trying to get our software on our Xerox data systems Sigma 7 computer working.
Number 4 off the production line. It was a brand new machine from a company that was very new.
Used to be SDS, and then Xerox bought them and so forth. And we had to get we had to design a hardware interface, and Mike Wingfield did a super job on that. Meanwhile, trying to get some software working was slower. We heard that BBN was having some timing troubles, and I thought, oh goody, that means that they'll be late shipping their machine. They fixed their hardware, their timing troubles. They put the machine on an airplane, and it showed up about 2 days early before the 1st of September. And my estimate of 2 weeks grace disappeared, and there was some pressure. I want to pick up on that thread and both open the scope a little bit and pick up on some points that you said, Len and Vint. You made reference to we had all these machines at MIT, and you could see that they're going to be connected together. And ARPA, originally the agency was named ARPA, and then it became DARPA, and then it became ARPA again, and now it became DARPA again, had within it, as a funding agency in the Department of Defense, had within it this office called Information Processing Techniques Office. And if we roll back time a bit before the 1968 RFQ into the sort of mid-60s, 65, 66 timeframe, the same perception that you alluded to, Len, was also quite visible and evident in this office. That office was funding advanced computer science research, and the idea of computer science research was not yet a clear-cut idea within the academic community. National Science Foundation was putting computers into universities primarily to support hard sciences, physical sciences, to do large-scale calculations. You had major computer centers. Computers were very expensive, and so there was a question of how to pay for them and how to meter out the time. And hence, the mode of use was batch processing. But in certain areas, and particularly in the areas that were supported by this office, by IPTO, interactive computing and the development of time-shared computers was far in advance of what was around in the rest of the community. And as a consequence of that, it was very visible that you had communities of people who were interacting, and two or three things were evident all at once. One was that interaction was much more productive in terms of human time, even if it was less efficient in the use of the computer. Another is that it created communities that could interact with each other. If you have 30 or 50 people who are using the same facility, it creates a natural community. And then the idea of interconnecting these computers so that you not only could get the resource sharing, which was alluded to, which might be more efficient, but you could also get collaboration. You could get collaboration across on the people dimension. People interact with each other. And you might have different facilities available on one machine or another, and you might be able to gang those together in ways that would give you novel computing. So all of those ideas were in the air. And it was that which was driving the idea that we should connect these computers together. Then that leads into, well, how are we going to do it? And the work that Len had done, the work that Larry Roberts had done, became very important. And Larry Roberts was recruited to come down to ARPA to make this happen. But the precursor of all that was this vision and determination. And there had actually been some earlier experiments trying to gang a couple of computers together, hook them up with intermediate results, some positive, some negative. And Bob Taylor, who was Larry Roberts' predecessor in IPTO, decided that the time had come to try to have this network which would connect the different research sites together, not solely for the purpose of experimenting with packet switching. And in fact, one could argue that the focus on packet switching was subordinate, or subsequent in any ways, to the initial motivation, which was we needed to get the people to work together, we needed to get the computers to communicate, and we wanted to have a way to do that. So that layer, if you will, of we're going to have computers connected to each other and the people connected to each other, was the driving force. You've heard a lot from Len and from Bob and from Dave about then the details of getting the groups together, developing the software, developing the hardware for the routers, which were called the interface message processor, or IMPs in those days. But at the end of the day, the question was, what are we going to do with this network? Yes, we have to build it. Yes, we have to test it. Yes, we have to measure it. Yes, we have to understand those dynamics. But you get all that to work, and what are you going to do with it? So one of the strategies that IPTO used, that Larry Roberts used, was to implant this network in the research community that was already being funded. So we had a series of computer science research places: MIT, UCLA, Carnegie Mellon University, Berkeley, Harvard, others, Stanford, and they were gifted this network, some more happily than others. Some felt that this was an intrusion in their carefully built up structure and weren't initially too thrilled with the idea that there would be others from the outside using their facilities, but others very happily interested in the ideas and the new technology. So as you've heard, UCLA was selected as the first site, and SRI, Santa Barbara, UCSB, and Utah were the next 3 sites. And it then became a natural issue of, well, okay, this is coming. The RFQ is out. BBN had got selected. They're going to build this thing, and it's going to arrive on our doorsteps. And Vint and I were at UCLA, and so we had to deal with what are we going to do with this. We met representatives from the other 3 sites almost simultaneously with the RFQ hitting the street in August, and we began to form a loose, very informal and unchartered coalition to think about what are the host computers, the computers that we were using for our research, what are they going to say to each other? Taking the IMPs and the subnet that BBN was building, hadn't been selected, BBN hadn't been selected yet, but the rough outline was clear. What are we going to do with this network? And so we chatted with each other intermittently. We met every few weeks, and we generated an informal set of notes eventually, trying to figure out from a clean sheet of paper what would be the architecture of the protocols that we would use to do that. And from those very tentative first steps, some structures started to emerge, and the structures were a combination of technical structures, protocol architecture, and a kind of social structure of how to work with each other, how to communicate, and what the process would be for arriving at conclusions with that. And I'll subside at this point, and Vint, you can easily pick things up from there.
Bob?
I would just like to elaborate on that a little bit. See, not everything was quite as smooth and straightforward as you might expect. In the early days of trying to get this network up and built, we did something back then, or DARPA did, to be specific, that would be very hard to do today. What Steve described as computer resource sharing was really the mantra of what this was all about. People kind of sort of intrinsically thought that if computers could interact with computers, a small set initially of people and machines and maybe a larger set later, that good things could happen. Today, some 50 years after we've started that, we still haven't achieved, I believe, even a small fraction of what people were thinking might be possible. We did some simple things at first, use the net to replace wires, more economical. But we were doing things that you could have done before, maybe at lower speed, maybe with more errors and the like. But even today, it's still a dream in the future. Today, if you put something like that on the books of one of the major funding agencies, you couldn't explain what you were going to do with it. What problem was it solving? I don't think you could fund it today. So that was one of the interesting conundrums from back then. The second thing is that even building this network, even though we got all kinds of people to work together, was by no means a straightforward and simple thing. And I think it's important in understanding history to know what things are just sort of engineering things where you kind of lay out the plan and you do it. Len described, what the inputs were to DARPA. And when the RFQ came out, they actually had some fairly high-level inputs. Half-second delay, reliable computing, all of that sort of stuff. But, if you were to compare it with, let's say, Kennedy and the moonshot, he had those kind of descriptions in the plan for going to the moon. Take a person there, getting back safely to the Earth, payload of enough to at least get a person there, maybe some other stuff. But it didn't say, how you would do it in detail, how to build the rockets, how to build the control systems. We knew in the early days that, the network would potentially be useful for the DoD if you could do it. Otherwise, DARPA never would have funded it in the first place. And yeah, Paul Barron had written some very interesting articles about what he called message address box switching. But that was before there were computers around that were practical to use. He was talking about hot potato routing from AM radio stations around the country. It wasn't really a viable net. No carrier would have ever done anything like that, and it was all sort of hypothetically, in case we were ever attacked in a nuclear scenario, we were already about thermonuclear war back in those days, at least at the RAND Corporation. So it was a very challenging and interesting time. The task that BB&N had was literally to do the design task initially, as Dave said, and then to actually build it. And the design task was not even a simple one. I'll give you two examples. One, in developing the network concept initially, we had a lot of discussions. Dave was part of it. Many people at BB&N. Should we make these nodes with hard disks, which is what DARPA was sort of expecting, so you could store a lot of packets? And we pushed back very strongly and said, no, don't do that. There's latency to store it. You know, who wants to build all of this storage inside the net? Push back and stop it at the source. So there was a set of discussions about that, and I think our proposal to literally do it in core memory was in fact the right one. Second one was even more controversial. There was a very interesting book that was written by Katie Hefner called Where Wizards Stay Up Late. It's great reading. I loved it. And Katie is a great writer. But she wrote an initial version of that, which I got to see very late in the game. And it had a whole description about the very issue of congestion in the net that I looked at that and said, Katie, that's just not right. And where did you get that? She said, well, that's what I understand happened. And I said, you know, in 1972 or early 73, when we went out to do the testing, Dave and I went out to
70. It was early.
70. That was 1970.
No, 1970. We went to UCLA.
That's right. It
when
was
you and I got there.
Yeah, and Vint was there too.
Yeah, 2 years before. 1970, we went out to test it.
Yeah.
And the thing we set out to do initially was to show that the way the network was currently implemented had the potential for locking up.
Yep.
And we did it in 12 packets.
Yeah.
Dave had it in his little
But if
book
I could
there.
just say a word, Bob had been talking to us about some of these things during the implementation in 1969, but we were very focused on getting something fielded, and we weren't listening too hard, frankly.
That's the first time you've ever said that.
I have said it before many times. And once the 4 nodes were installed, then we were able to hear. And in fact, we went out the test. Bob can say more about that. But an important point is we had an initial demonstration, but we spent the next several years correcting algorithms,
Yes, you did.
Replacing algorithms that didn't work so well, replacing algorithms that worked pretty well but not at high load, and so on. So the underlying IMP project was an ongoing job in parallel with the hosts all getting up, and from my view, it worked really well. You know, we communicated back and forth. You know, when the big bug was found that Bob pointed out, and it locked up, I sent a message out to the host saying, please don't do that until we get it fixed. And they didn't do it.
So just to fill in one more detail here. In, how was it, 1968, I get my dates right, while I was still thinking about networking, I thought it would be really nice to have a simulation program to test various algorithms. And I worked with a fellow named Warren Titleman, who had been one of the implementers of something called BBN Lisp, which later morphed into InterLisp, to write a graphics simulation program. It ran off of the BBN machine. They had a pager. It was a time when people weren't doing graphics on time-sharing systems. They mainly had Model 33 teletypes. They were printing things out, it was just character strings. And we actually built a really lovely simulator, so you could say, you know, when the packet is at this node, apply these algorithms, and it was all done at a very high level in Lisp. And he had to create a display version of Lisp to do that. And then the fellow I was working for was Jerry Elkind, had funded the work on that, but when we won the contract, Jerry came to me and he said, you know, if you want to work on networking, you're going to have to get the money from Frank. because the contract was there. You didn't want to take it out of any of the other contracts. And so I had a decision to make, because Frank had basically said, we're not going to worry about the things that you worry about. It was what Dave was just referring to.
Yeah.
And not listening about congestion and the like. His argument was like, you know, packets are not going to congest. We won't get deadlocks. It's like, should people in this room worry if all the oxygen molecules were to show up in the corner of the room over there and we'd all suffocate? It's not going to happen. It doesn't happen. And besides which, if it ever did, we could go back and fix it, maybe put in a fan or equivalent. And so it got left out. And to me, that was a real frustration. So when Dave and I went out, that was the first thing I set out to do. When Katie wrote her book, she described it this way in the first version. It didn't show up in the final version of the book. What she said was, Dave and I went out and we discovered when we were out there that the network could lock up.
It's the other way around.
She described exactly the inverse, like we had no...
We confirmed Bob's belief.
Yeah. So, and I couldn't convince her at the time that she had it exactly backwards. And I said, there's no proof that you ever even did that. I said, yes, there is. And I pointed to a paper that Warren and I wrote describing that display program, which was in a public conference. The publication was at Princeton University in mid-'69. So when she looked at that, she said, I guess I can't resolve it. And she literally deleted that whole part of the book. So it doesn't show up
I've got
anymore.
two hands up over here. Actually, which one, Len, I don't know what either of you are going to say, so I don't know which is closest to the
We're
topic.
not sure either, however.
All right, go ahead.
Picking up on what Bob said, I had written a simulator in 1962, which was a graphic simulator with light pen and all the rest and moving cues. But the object was actually to worry about something different, which at the time was not clear. If you had an uncontrolled network with these packets and messages flying around, would the thing settle down? Never mind lockup, which was another kind of issue. Did this thing even work? And the simulator was able to show, as well as the theory, that it would work. The second thing I want to point out to is something that both Steve and now Bob has referred to, and I think you did, Vint. This idea, how did all this wonderful work take place, this magic? What was it about that period? And it started with the culture at ARPA of how they funded these projects. They would go to a researcher and say, you're a great researcher. Here's a pile of money for a long period of time. Do something in which you're expert. Shoot high. Failure's okay. We're not going to watch you. Go ahead and do it. Now, with that kind of enablement, great things did happen. And in fact, the idea that Steve was talking about, the idea of sharing computer resources, was in fact the underlying idea of sharing communications resources out of the time-sharing world. In fact, the early internet, the ARPANET, was the first of the shared economy systems, which we now call Uber and Airbnb, etc., sharing things when someone else is not using it. But continuing with this philosophy, this funding culture, when the PIs got that money, what did they do with it? They went to the graduate students and said, look, we got a problem to solve. Go solve it. We're not going to tell you how to do it. Try. Failure's okay. Shoot high. Run with it. And in fact, that permeated, and then they started forming these groups, and it was wonderful the way it picked up. But as Bob says now, that kind of capability is just not there. There are too many restrictions, confinements on how funding is done. But in those days, it was enabling, and it was unbelievably productive.
Steve?
I'm going to shy away from the funding issues for a second, but an anecdote related to the store and forward lockup issues and the congestion control. So you've heard about the design process in 68 and 69, the testing and measurement that Bob and Dave did when they came out to UCLA in the early part of 1970. In mid-1971, I interrupted my graduate studies at UCLA and joined the office in Washington and in Virginia
the ARPA.
at ARPA. And I had been very active in helping in the design process for the host software, and also in providing specific advice to individual sites on how to write the software in their hosts to connect up to the ARPANET, and in organizing others to help do the same. So I arrived reported to work in July 1971, and 10 days later, my boss, Larry Roberts, sent me down to Oklahoma City to interact with some Air Force people at Tinker Air Force Base. He had arranged that they were going to run a side-by-side test comparing the ARPANET to the existing military communication system called Autoden. And the folks at Tinker Air Force Base were going to, get an IMP, and they were going to connect one of their computers to an IMP there, and there was going to be another one at McClellan Air Force Base outside Sacramento. And I was supposed to advise them on how to write the software that they needed to do. So I recognized that the desirable thing was that we wanted to make the ARPANET look good, and so we wanted the maximum throughput. There had been a regimen related to the comment that Dave Walden just said about don't do this, of limiting how much you send in a particular conversation. I was not tuned into it because my primary attention was I was more focused on artificial intelligence and other things. And so I advised these guys that they should open up several parallel connections and throw as much data forward as they could, and that would make it all look good. So they listened. They were very sharp Air Force captains who were also graduate students at Texas A&M, as it turned out. And over the next several months, with a couple of visits, they eventually got their software up and running. I was in a meeting at MIT in a closed conference room, and I got tapped on the shoulder that there was a phone call for me. And it turned out that these guys had turned on their software in February of 1972 now, and 4 seconds later, the entire ARPANET crashed.
I ended up with a notebook full of stuff from Tinker and McClellan, because I was the guy who was writing the software in our host machine at UCLA to actually capture a lot of that measurement stuff. And I don't know what happened to that notebook. I got to continue this a little bit. I'm sorry.
A little bit. So I was pulled out of this meeting, and I picked up the telephone, and there was a colleague from BBN, Severo Ornstein, yelling his head off. "Why'd you do that?" And I said, "Hi, Severo, what's up?" And eventually, as he calmed down, I got the picture of what happened. And he said, "You did this on purpose." I said, "Well, not really." He said, "They said you smiled when you said it." I said, "Well, yes, I thought it was a clever idea." And he's still yelling at me. I said, "You know, Severo, I'm a civil servant. This is really more my network than it is yours." So we got past that. But the issue of what do you do with overload and congestion, and particularly these routers, these IMPs, had a limited amount of memory. Memory was very dear in those days, and so buffer space was a very useful, precious, resource. And how to manage that and get it just right was one of the big challenges. They obviously got past that, and the network continued to operate.
Well, the problem was, we were making measurements at UCLA, and measurement messages happened to be 2 packets long, which requires a process called reassembly. And at that time, the storage had been doubled, pointers were not allocated, there was a hardware misjudgment. And every time we turned on measurements, the network went down. These guys yelled at us. They fixed it. We turned on the measurements again, took it down. They yelled at us a second time. And finally, we figured out what the trouble was. There were lack of pointers, etc. But we had a lot of fun back and forth.
We did.
Breaking, fixing, breaking, please fix. Fix it quickly. Anyway, that was the iteration.
There were 2 things I wanted to mention. One is that clearly for the DARPA project, this was important so that you could at least get reliable and efficient and relatively low-cost communications. But the thing that made packet switching visible in the public space was a demonstration that we put on. I was asked to put it on by Larry Roberts originally. Steve actually doesn't recall, but he called me later and said, Larry wants to do it at the Washington Hilton at the ICCC event. So we did that, and it was a kind of a week-long event with everybody who was anybody in the networking field showing up there for a week, housed in the ballroom there. We had an imp in the center of the ballroom. We had a lot of terminals around and computers all over the country. There were roughly 40 of them or so at that time. And you could sort of see what it was all about. We had a contingent from some of the commercial folks there, didn't quite believe it, but it really put it on the map as a viable technology. Many years before, they were writing about how this was kind of radical, it would never work. We heard people proclaiming packet switching didn't obey good data principles, whatever those were, but you'd hear things like that all over the place. The second thing is the implication that it had for DoD. Remember, the funding came from a DoD budget, and DoD was very interested in communications, but they had invested in something called Autodin 1 for communications way back, and Autodin 1 was a kind of a message transport system which involved tapes. Very slow, and they wanted to build a new system. They came up with something called Autodin 2. It had been proposed out of the Defense Communications Agency at the time, and it was their first proposal was to build a fast circuit switching system, which had all kinds of issues when speeds went up enough as to whether it was the right long-term choice and whether it was really a good choice for computers at all. And that ended up in a dialogue between DCA and their supervisory body in the Pentagon, which was, I think, C-Cubed-I or DTAX or ASA, one of those names, C-Cubed-I, I think, at the time. There was a report commissioned by C-Cubed-I, and maybe it was commissioned by DCA, but it was asked for by C-Cubed-I, and they gave it to Lincoln Labs. And so Lincoln Labs wrote a report. It was essentially honchoed by a guy named Erwin Lebo, who later became the chief scientist at DCA, and it basically said, why don't you build a thin line system based on ARPA's packet switching technology rather than spending a lot of money, and just let that be just demonstrate whether it can work, and if so, use it. You don't need to spend that. It was rejected inside of the Defense Department because how could a bunch of researchers know how to build a real military system? And so they didn't go that path. They put out a bid, the contract was awarded to build an Autodin 2 system based on packet switching. So it had the effect of changing the mentality in DCA, which was not a trivial accomplishment. And they awarded a contract that eventually they spent, I think, more than $100 million building. The decision-making that led to that was kind of interesting, and I was then asked in my DARPA role by Lee Pascal, who was then the director of DCA, I think a 3-star general, if I would lead a blue ribbon panel to evaluate the inputs that they got. And I remember after we did that, and I met with him, I said, I have 2 topics that I'd like to talk to you about, but I don't know if you want to hear about both of them. And he said, what are they? I said, one is whether you should have done this procurement in the first place, and number 2, about the comments that you got on all the proposals. He says, I don't want to hear about the first. He goes, it's already been out there. The reason we did it is because I'm trying to deal with the people here who have their own set of needs and requirements, and this was to address them. I don't want to hear that. So we then commented on the specific proposals that came in. He listened very carefully. They let the contract out, and the party that won it thought they'd build it and then they'd have maintenance requirements going forward. At the end of that contract, the DoD accepted the system that they built, which involved, I think, 8 hubs, each of which was staffed by 8 people times 3 shifts. So they had a lot of people. It was very expensive. It was about 1/10 the throughput of the ARPANET and probably many times the cost. They canceled it 1 day later, and they went back to essentially what was Erwin Lebo's original proposal. So it had a big effect on defense, not only in terms of what they did, but how they got there. So, I mean, it was a major DARPA contribution that really changed the way DoD works. And today, that defense data network is still in operation.
So I want to come back to something, if I could, because we're going to run out of time. This is to take you back to the gestation of some of this work. We've already alluded to the fact that the resource sharing motivation came from a belief that computers could do more than simply compute numbers. So J.C.R. Licklider at MIT, who was the first IPTO director, was a psychologist who had an inherent belief that computers could augment the ability of human beings, and he had found a kindred soul in Doug Engelbart at SRI International, who had a similar view that human intellect could be augmented by the use of computers doing non-numerical kinds of computation. So the second node of the ARPANET was SRI International, and the place where it landed was in Doug Engelbart's Augmentation Research Center. And that takes us to the headline of this session, because that was the second node that went up. Before that node was in place, the IMP couldn't talk to anything but itself. I mean, we were able to make packets flow from our Sigma 7 machine back into itself, but that was not a very exciting network, to be honest. So the first time that the two nodes of the network could be used to connect the two hosts that were in place at SRI and UCLA was on October 29th, 1969. And so Len had one of his students, Charlie Klein, doing a test. It was Bill Duvall, who was up at SRI International.
I think so.
Yes, yes.
And so what happened, Len?
So as Vint described, we now had a two-node network. One node does not make a network, but two does. And as Steve had said earlier, the idea was to be able to use someone else's machine as if you were local to that machine. So you sit at one node, you log on through the network to a second node and use the resources at that node as if you're a local user. Two nodes, let's try it. So Charlie Klein, we were down there in our computer room, we were going to try to log in from UCLA through the network to the SRI host. All we wanted to do was log in. And to make sure this worked now, Charlie was down at our location. I was there with him. And Bill Duvall was up at SRI. Now we're going to try this new thing called packet switching. We have no idea if it's going to work. We hoped it did. So to be sure, we had a telephone connection between Charlie and Bill. Now look at the irony here. We're using a telephone connection to prove a technology which is going to eat the lunch of the telephone network. And eventually it did. So all we want to do is log in. Now to log in, you have to type L-O-G, and the remote machine is smart enough to know what you're doing. It types the IN for you. So all you have to do is type L-O-G. So we're prepared to make this monumental test. Now let's compare it to history. The first telegraph message. What did Samuel Morse prepare? What hath God wrought? A good message. How about Alexander Graham Bell? Come here, Watson, I need you. Neil Armstrong, a giant leap for mankind. Those guys were smart. They understood public relations. They understood media. They had the press, a camera, and all the rest. We didn't have a camera. We didn't have a sound recorder. We just had two guys, telephone, make a connection. So Charlie types the L. He says to Bill, you get the L? Yep, got the L. Get the O? Got the O. Get the G? Crash. Network went down after LO. So, two comments. First of all, what was the first message ever on this network? Lo, as in, lo and behold. We added that later. But it was the most prophetic, most profound, most succinct message we could have asked for, and nobody knows it. Hopefully the title of this session will help spread the word. But it was a very effective message. Now, the question is, what broke? Why did it fail? Well, it wasn't our Sigma 7, and it wasn't our IMP, and it wasn't the first piece of the backbone network line from UCLA to SRI, and it wasn't the SRI IMP, it was the SRI host. So it was their fault, it wasn't ours. And we can tell you why it failed, but the first message ever was low. September.
So, Vin, can I ask Lynn a question? Is that appropriate for this? So we spent, what is it, 2 years or thereabouts after that trying to develop protocols to embed in the operating systems to actually make the network work? Yeah. What protocols were you using back then?
We were just none at all. We were basically acting There was a host IMP protocol at the time, and an IMP protocol, and we were just trying to log in locally to that machine. That SRI machine didn't know we were coming into the network.
It was an ad hoc lash up of a kind of just telnet-like. So at UCLA it was the client side, which was easy, and then SRI had the stronger burden of having the service side, and they had added software to their operating system to bring the network messages in and treat them as if they were dial-up messages. Mm-hmm. And the glitch was that their operating system, which was very smart, as Len said, would fire back GIN after it saw the LO and the G. But the software that they had added for the purpose of running this little test was not expecting more than one character in response to a character typed in.
So it was a 10X machine at SRI.
It was an SDS 940.
940.
940?
940.
It was an SDS 940 there.
Yeah.
Running, okay.
But it had some very sophisticated programmers. Jeff Rulison was a crackerjack in Bill Duvall and others, and it was just a relatively minor thing, but it creates a nice anecdote that make a full meal out of here.
So I want to come back to origins for just a second, because none of this, I think, would have happened if it weren't for the fact that computing was getting less expensive. Machines used to be batch-oriented machines. You submitted your big deck of cards, and 24 hours later you might get something back. Time sharing arises at MIT around 1961 or so with John McCarthy and some of his colleagues, Corbato, I guess, and some of the others. McCarthy brought that idea to Stanford University about the time that you went to UCLA. He came to Stanford. But this idea of sharing the machine and making it look like you had a machine all to yourself, but it was actually time sharing, turned out to be one of the key reasons why this whole project made any sense at all, because it meant that multiple parties scattered around the network could be accessing the resources of any one of the institutions concurrently. And so the time sharing notion was part and parcel of motivation for building the network and making it interactive. And I think that, once again, is another example of timeliness of some of the technologies that came together to make this project useful. So I think I want to spend some time, we have a little here, I want to spend some time with Steve now, because Steve's work at the host level took us into territory that no one had ever been in before, which is trying to get machines of different brands to talk to each other. These machines had very different characteristics. Some had 16-bit words, 32-bit words, 36-bit words. So Steve led the network working group to develop the host level protocols. And I don't know whether you want to comment at all on what you learned from that, but I know that it had a big influence on the architecture and design of the internet protocols later.
Well, thank you. So that's exactly right. As I said earlier, those of us who were at the different sites started to talk to each other, and without a grand plan, started to tackle the problem of what should our hosts say to each other. We knew, of course, that there were two functions that were very obvious. We'd want to be able to remotely log into a remote machine, and we'd also want to be able to move a file wholesale from one machine to another. We had some brief discussion about email, and we thought it was pretty low-key and uninteresting, too simple in a way. It, of course, took over everything until the World Wide Web became even bigger. But right from the beginning conversations, we had in mind that we didn't want to underplay the structure. We wanted to provide building blocks that you could do things that were not necessarily yet envisioned, but would leave room for others to build on. And so we, as we met, and we kind of self-organized. A few people from each of the sites started to interact, and first decision we made was to visit each other's sites and get to know each other better. And we knew that that simple decision was running counter to the whole idea of a network which would make it possible to collaborate without busting your travel budgets. And the first thing we did was bust everybody's travel budget. Yes. Len had to go get some more money just so I could go traveling around. I was very proud of that, actually. So we looked for a framework for these protocols. I don't think what we did was spectacularly clever or elegant. We tried, and there's certain parts that I could go on at length about. Dave Walden and his colleague Will Crowther at BBN were working very focused on getting the underlying network working, but they watched what we were doing and sent some critical comments at one point, and I said, yes, well, okay, and then we just proceeded straight down the path we were on. The really important part of all that, however, is that as the ARPANET morphed into or became the seed that led to the internet, and I want to come back to that in just a second, and then Vint, I'm sure, will say a lot more about it. But the idea of these protocols sort of existed on their own at a level above the basic packet switching substrate that or subnet that was being built, and created a structure that persisted and expanded rather elaborately over, what now, 50 years.
5 decades, that's right.
Amazingly so. And so there are protocol designs. And how many protocols are there? It turns out to be a large number of protocols, more than one would guess. I heard a deputy director at NSA describe going into federal court and trying to get a warrant and saying all the things that they had to measure and all the things they had to probe, and the judge is asking very pointed questions. Well, how many protocols are there? and giving him a hard time. And he describes, well, they had to go away and they had to count them, and they came up with 100+ protocols, and they came back with a very precise number. And then a short time later, they had to go back for another meeting with the judge on another warrant, and they knew that they had to come up with the precise number, and they said a different number. And the judge said, well, how'd that happen? Why are there so many more protocols now than there were before? It's a very active process. And the judge said, was who let that happen, actually? But there is the sort of ground-up process, bottoms-up process of creating protocols. So you have host-host protocol, you have the Telnet, and you have TCP and IP and HTTP and email protocols and DNS and so forth. And those are just the most visible of what are really hundreds of protocols that do a variety of different things. And what's critical is that there's a process that is very active. The Internet Engineering Task Force continues to roll along after multiple decades and meets 3 times a year physically and has 100+ working groups all of the time. And that developed a life of its own. And at the same time, the ARPANET triggered a intense desire for other networks and consequently the need to interconnect those other networks. And that, and I'm going to intrude in your space a little bit, but that need to interconnect networks was really threefold. There were other technologies developed within IPTO, packet radio technology and packet satellite technology. So even within one funding agency, even within one office, the need to interconnect these disparate kinds of networks. Then you had within the U.S., you had different agencies. You had NASA and Department of Energy, for example, and NSF, all of which wanted to build networks and a recognition that these needed to be connected. And then, of course, from a global perspective, you had countries. At UCLA, while us graduate students were just sort of wrestling with what do, we were visited by the Canadians and the French and the British, and it was evident that it became a national priority. We too have to have a network. So you had this push to interconnect networks and to make a very long, complicated, and probably thrilling in the end story. The internet emerged out of that. Vint will make much more sense out of all that. But the point I want to make is that you had, from this ARPANET development process, you had not only the proof that packet switching was efficient and could be made to work and be made to work reliably and so forth, But you also had this protocol layer on top of that persisted and became a life of its own. And then on the packet switching level, you had the creation of multiple networks and a need to have these different packet switching networks interact with each other, even though each one of them was under its own administration.
So it didn't actually have to be that way, though. Bob will remember that certain different kinds of transmission systems were incorporated into the ARPANET itself. In particular, there was a dedicated satellite hop that connected the ARPANET from the US all the way into Norway and to London. And it was possible to have incorporated mobile radio, for example, into the same architecture. But Bob had a different idea about that. And so maybe you could tell us why you saw the value in breaking out the different communications media into distinct networks instead of trying to incorporate it all into one.
Well, the thing you're alluding to, I'll talk about explicitly, but let me say part of a more general notion was that if the networking capability was to expand around the globe, it couldn't go the way DARPA had originally formulated it. And, you know, Larry Roberts was much more modest than most people probably realize, because he played a very important role in getting the ARPANET going and sort of masterminding that whole thing. But, you know, when I think it was you, Len, myself, and Larry got the Draper Prize back some number of years ago, when they had a session after the fact at Draper Labs. And Larry got up and he made a comment that I thought was pretty amazing. He said, you know, he always knew this technology would be important. He said, but the path that they were on never would have gotten it anywhere, except for the fact that the protocols that we came up with were what enabled different administrations and different people to build it independently. So he graciously gave a very nice compliment to the work that was done on those protocols at that time. But so that was one phase of it that I saw. Number two was that I was pretty convinced that we needed something beyond the NCP protocol if we were ever to get into the wireless area, mainly because you could get lost packets and the like, mainly because you could be behind tunnels or in tunnels behind mountains and the like. So that was another one. And then there was a specific instance that we ran into, which was trying to extend the ARPANET over to Europe. So the first link was a dedicated link from actually Etam, West Virginia to Tanum, Sweden, to connect to a Norwegian seismic array effort. And then we managed to convince the combination of NTA, which was the Norwegian administration, and the British Post Office to build a link down to London. And so they paid for that, a 9.6 kilobit line. And then from there, Larry had made some arrangement to build a 2.4 kilobit link to Stuttgart in Germany, where the European Command Center was. And that was almost the showstopper that broke it, because the way European rules worked, if you had a node like an IMP or any piece of equipment to which two carriers' lines were connected, the carriers involved all had to agree. So if you took a link from the US to Norway, just those two carriers had to agree. When you took it from Norway to London, and that was a British Post Office, now all three carriers had to agree, and that happened pretty easily. When we tried to get, or Larry tried to get a fourth line from London to Stuttgart, the Post Office and the Deutsche Bundespost agreed, the Norwegian Telecommunications agreed, but the US carrier did not agree, because they said we could just give you a line directly from the US to Stuttgart. And that was expensive. And the agreement that Larry had worked was actually for a military line from England to Stuttgart. So not only were the CCITT regs a problem, but the way it was structured, they now had military and commercial. And I remember all the interactions with the British Post Office at that time. I mean, even the Queen couldn't get them to do a cross-connect between the military side and the civilian side. It was just not going to happen, period. So it was a showstopper. We finally managed to convince the British Post Office that we really needed this, and they didn't have any capacity on the civilian side. 2 years later or 3 years later, we got a 300 baud line for 10 times the price. And the party in the U.S. that wanted it was the director of DARPA, Steve Lukasik, and he was gone from DARPA before it actually got put in. So he was having no part of that either, and that led us to go down the packet satellite route, because if we used Intelsat, which was the only satellite system that was really viable then, we had no domestic satellites, that already had built-in agreements between all of the parties to allow sharing of the satellites. And so then we just had to negotiate the tariffs, because they only had point-to-point tariffs and unidirectional broadcast tariffs. So we had to get a tariff that would let anybody sort of deal with it like an Ethernet in the sky, which we did. And there's a paper that I wrote on the politics of this that was in the 1979 NTC conference, I think maybe here at this hotel, or maybe it was the one next door, that laid out the kind of the negotiations about the politics.
So, but I'd like to stay focused on the technology for a second here, because the fact that that you started a mobile packet radio program, and Larry started and you managed to continue the packet satellite program as distinct networks, were, in my view anyway, partly motivated by trying to use this technology to assist the Defense Department in command and control. And in order to put computers at work doing command and control, that meant they had to end up in ships at sea and airplanes, mobile vehicles, as well as fixed installations, which is where the primary computers of the ARPANET were. I mean, they were in fixed locations in air-conditioned rooms, and they certainly didn't get up and wander around. So at the point where you are entering into this multiple network environment, you sort of induce the problem of having to find a way to interconnect these networks, because they were distinct. And even more interesting, I think, is that Xerox Palo Alto Research Center, which is a few miles from my laboratory at Stanford, in May of 1973 invented the Ethernet. And the Ethernet had the property that it was a dumb piece of coaxial cable, which meant that it wasn't smart enough to retransmit packets on errors. In fact, the packets would collide with each other and they would be lost in that common transmission medium. So that was an instance of a very lossy network which had no ability to recover on its own. The computers at the ends of the various Ethernets would have to be the ones that are recovering. Packet radio environment had a similar problem, because the mobile vehicles had changed their connectivity. Packets would be transmitted but not necessarily heard. So we were surrounded by communications technologies that had lossiness as part of their characteristic. So the difference between the original ARPANET protocols that Steve developed with the network working group, and relied fairly heavily on the underlying reliability of the ARPANET, could not be applied to this much less disciplined environment, which led to reinvention of the end-to-end protocols, which we call TCP/IP.
Let me give Steve, credit here for a comment that he once made to me. I had said to him that the real benefit of the TCP protocols that we developed was to deal with that issue, in part, not entirely, because addressing was also a big issue. But he said that the reason they did the NCP protocol the way they did, I'll give him a chance to contradict that if I'm stating it wrong, was because BB&N had told him the network was going to be perfectly reliable, and therefore they didn't need to do that. Otherwise, he might have gone a different way with NCP. Well, you can give it to Steve to comment, or whether you think I stated that correctly or not.
Well, yes. I like all these guys, and we've all known each other for a long time and have very high mutual respect. The BBN crew, Bob and Dave and the ones who aren't here, Frank Hart, Will Crowther, and so forth, as I mentioned, were very focused and very measured in the way that they developed the network. us graduate students from these other sites were much looser and not as well organized. We had our first interaction Valentine's Day 1969, if I recall, in the middle of a pretty terrible snowstorm in Boston. We had some of our tentative ideas that we brought to the meeting, and one of them was that we were going to have checksums at the host-to-host level. And Frank Hart reacted quite vigorously, quite strongly. He said, "You're going to make my network look slow," and he counseled us against checksums. And we didn't have in mind that we were going to retransmit. We thought the network would be reliable, but we wanted to detect configuration errors. Actually, the suggestion from Jeff Rulifson, who had a lot of experience in operating system and file system design, said, if you can detect errors at the different layers in the architecture of the software, then you'd be way ahead of the game. So we had that penciled in our discussion, and Frank pushed back quite hard on that. There was a huge difference in stature. We were youngsters, and he was an adult. It was the short version. And I challenged him a little bit. I said, so I understand you've got strong checksums between the imps, and you retransmit, and so I have no issue there. But I said, you've got this wire that's going to connect the imp to a host, and it's a bit serial line, 100 kilobit. How reliable is that? As reliable as your accumulator. Rings in my ears all these years later.
Really?
We later put checksums in a lot of places in the program because memory bits drop out and so on.
One of the, as it turned out, it would have been better. It was already clear to me. I was in the middle of the design of the basic host-to-host protocol that later became known as NCP. TCP was the replacement of that. I would have been happy to see TCP-like protocol earlier, so I had no objection to phasing out NCP and going over to TCP. This is part of the maturation, part of the learning process in the whole thing. Indeed.
So we have a few minutes left, and we can do one of two things. We haven't really touched very much on the evolution from the end of the development stage of ARPANET host protocols to the evolution of Internet. We can't do that in 10 minutes. I do want to at least draw attention to one important theme in the evolution of Internet, and that's the role that the National Science Foundation played. I was reviewing a lot of their involvement, and they got into this around 1980. This is well after the ARPANET had been turned on in 1969. They became interested in, after they saw the various departments that DARPA was funding, making heavy use of sharing of resources, decided with the 4,000 or so universities that they support that they should get them hooked up as well. And so they began working on a computer science department network around 1980. Then
called CSNet.
CSNet. And then in 1985, they were working on supercomputers. They were funding supercomputers and realized that in order to make them useful, they would have to be networked, and that the universities would have to have a path to get to those supercomputers. So they decided to build a backbone network like the ARPANET, which they called NSFNet. The first one was a 56 kilobit system that instantly congested, not because of a protocol problem, but because of the demand.
Right.
So then they tried again around 1986 or 87 or so with a 1.5 megabit version, which rapidly evolved to a 45 megabit version. They made some other really interesting decisions. Because the Internet architecture allowed multiple networks, they decided instead of having 4,000 universities demand service of one NSFNet backbone and drive the operators of that backbone crazy, they said, why don't we build intermediate level networks? So they had 8 regional networks that would service the universities, and then there were only 8 customers for the NSFNet backbone, which made life easier for them. So they induced a multi-network environment very early on in their planning. And then when commercialization started to happen in the late 1980s, they realized that they didn't need the backbone that they had built, and they shut it down in 1995. Yeah. But they built these network access points, or funded them, so that all of the intermediate level networks that had been connected by the NSFnet could be interconnected at these network access points, so nobody lost connectivity. So I want to emphasize that the sequence of decisions made by a research organization, NSF, in some sense propelled a lot of the commercial development of the internet by the decisions that they made.
Mm. Yeah, I would add to that, you played an important part in that whole activity as well, as I recall. I got a call from a fellow named John Pasta, who was at NSF, and in the 1970s, I think maybe because of the lingering effects of the Vietnam War, discussions that had been going on, particularly in the academic community, the relationship between ARPA and NSF had withered, I would say. There was not much going on between the two. And so I was running IPTO at the time, and I think John may have had a similar position in NSF, if there was a similar position. And he said they were holding a meeting at the University of Wisconsin. Larry Landweber was going to host it, and was to sort of talk about their networking plans for the future. NSF had tried to build a network called FedNet in the early 70s, and it had gotten shut down by the government for a variety of reasons, but it wasn't really clear that it was going to be controllable the way DoD could control a network, that it might expand further. So the Congress did not fund that network, but NSF was trying to figure out what to do for the research community. Because they started out with the assumption that even though the ARPANET was a big success at that point, NSF couldn't get on it because it must surely be restricted only to military parties. Wasn't true, but so we had this meeting, and I went out, and I thought it was an amazing turn of events because it was opening up potential for dialogue. And I could only make a day trip, so I went out in the morning and came back, but they basically started out by assuming they had to build their own, and they were going to do it on a commercial net that had just been available to them called Telenet, that Larry Roberts had actually left ARPA to become the second president of. So while I was there, I challenged them on them. I said, what makes you assume you can't get on the ARPANET? So, because we know it's a military net, we can't get on. I said, look, I'm not prepared to say that's the case. Nobody's ever asked. If you wanted to make a request, I'm pretty sure you could get approval to get on, so think about it. So after I got back home, they came back and they actually made a request to put 4 nodes on, and one was, I think, at University of Washington, Purdue, Delaware, I forget, somewhere in the Midwest.
Wisconsin, I think, was on too, University of Wisconsin.
Maybe Minnesota, I'm not sure. And so I remember having those discussions with CQI in the Pentagon, and they took the very firm view that, look, if that's what you want, fine, but make sure that the Russians can't get on, or something to that effect. I mean, it was, and so I went back to NSF and made the same kind of comment to them. Anyway, they ended up funding 4 nodes. It all worked out. And the reason I know is I sent them a letter and basically said, you have approval to put these 4 nodes on, and we told them what the pricing was. Back in the mail comes a postcard from NSF saying, congratulations, you've been selected as principal investigator on your proposal. So they treated it as a normal proposal that went in. And so that happened, but they only funded 4 because they thought the cost of doing it was too high. And they instead went with a Telenet connection, which broke into 2 pieces, one of which you handled, which was how were we going to make this happen technically. The other was the politics of it, because they felt like if we were going to connect ARPANET to Telenet, that all the Telenet costs associated with the ARPANET should be paid by DARPA, but none of the NSF costs for using ARPANET should be paid by either NSF or anybody else. And I said, well, that's a bad assumption. I think we should just not worry about it. You pay the Telenet related costs, we'll do the ARPANET one. Can't do that. And so we ended up saying, okay, then the defense policy, which came back to them, was that we will charge you exactly what you charge us. And he said, well, then what's the point of it? And we said, exactly. And so that's how it ended up. That's how it ended up working out, and that worked out fairly well for a while. When they decided to go link the supercomputer centers, that was a whole other kettle of fish that I won't go through all the details. It took some strange turns, which eventually had NSF wanting to work very quickly into a defense regime that was almost required to work slowly because of all the demand on them. They were growing the DDN from 50 nodes to 4,000 nodes, and then NSF wanted to put a few more in with priority. It couldn't work, and they went their own way.
So of such bits and pieces is history made. We've run out of time, but we all thank you. I want to thank the panel very much for all of your comments, and thank you for joining us this afternoon.